Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to be reviewing logarithms. Now the trick with logarithms is to recognize that they are also exponents. So we're going to spend the first part of the video switching back and forth between the logarithmic and the exponent form, and then we'll work on solving for x. Let's get started. All right, let's learn how to solve logarithmic equations and how they relate to exponents. So if I have an exponent that looks like this, I can actually rewrite this as a log. Here it is right here. So you'll notice that my variables change places a little bit. My b down here, which is called my base, comes from this b here. My y value goes right next to my log, and this now becomes equal x. So what I've done is I've taken this x out of the exponent, and I've put it right here alone on the right-hand side of the equation. This is what makes log so powerful, because sometimes it can be difficult to solve for this x. So let's look at a couple of examples. All right, so here is my first example. Now, looking at this, you can probably solve for x in your head. Yes, x equals 4 here, but you might not see that immediately, so it can be helpful to rewrite it as a log. So here's this exponent rewritten as a log, which means you can notice that I have x solved for right there. So I can use my calculator, putting log base 2 of 16, and I will get x equals 4. Now something I want to mention is this is log base 2. If you use the log function on your calculator without specifying that it is base 2, it will automatically give you a base 10. So just be sure you're using your calculator correctly, and it's great to use an example like this because you know the answer should be 4. So if you're plugging this in and you're getting a different answer than 4, check and make sure your base is set correctly. Let's take a look at another example. Okay, so here we have 27 equals 3 to the x. Again, this is one that you could maybe figure out on your own. But if we rewrite it as a log, you'll notice we've already solved for x. So you can simply take your calculator, again, make sure you're using a log base 3 of 27, and you will get x equals 3. Let's do one more simple example. Okay, so let's say we've got this equation right here. Again, we want to solve for x, but it's in the exponent. This one might not be quite so obvious to you. It depends on how comfortable you are with scientific notation. But rewriting this as a log right here, again, it solves for x. Now, the nice thing about this equation is this is log base 10. So if you're just using the log function on your calculator without specifying your base, it will automatically default to log base 10, which gives you x equals 9. Now, yes, you did notice that correct. This exponent is equal to what x is here. This is the really cool thing about scientific notation. We're going to see this again. What if you didn't need to solve for x, but you needed to solve for y? So let's take a look at this example right here. You'll notice my variable is y, and it's right here. In the previous examples, we were solving for x. Well, again, I can take my log form, switch it to the exponent form, and now this equation is much easier to solve because now my y variable is already solved for. And of course, 5 squared is just 25. Let's take a look at another example. Here we go right here. Again, you'll notice I'm trying to solve for y, but it has not been isolated yet. Let's rewrite this as an exponent form. Here we go right here. Again, 8 to the 4th is easy to put in our calculator, and we get y equals 4,096. So it's very helpful to be able to take logs either to their exponential form or take exponential form to logs, depending on what you want to solve for. Now let's talk about specifically how we use logs in chemistry. So we usually use these with acids and bases. Don't worry if you don't know anything about acids and bases. We are simply talking about the math here. So what I want to point out is our exponential form here looks very much like our chemistry equation here, where we're converting between a concentration and a pH. But I can also rewrite this as a log form. So again, you should notice how this looks very similar. Again, we're using log base 10 here. So depending on if you want to solve for pH or if you want to solve for concentration, you're going to use either the top form or the bottom form. So let's work a couple problems. Okay, this first question asks what is the pH if the concentration is 1 times 10 to the negative 5th. So I am solving for pH, which means I want to use the pH form of the equation. And I can simply plug in for the concentration, which was given to me. and plugging this into my calculator. Again, the nice thing is this is log base 10, so your calculator should default to log base 10. This gives me a pH of 5. Okay, let's take a look at another problem. Again, this is asking for us to solve for the pH, and it gives us a concentration. So I'm going to use the same form of the equation. So my pH is going to be my inverse log base 10 of 2.5 times 10 to the negative third, which gives me a pH of 2.6. Now, something you may notice, especially in this first one, we had an exponent of negative 5, which means we ended up with a pH of 5. That is not by accident. Remember, this log form can also be written as an exponential form. And also notice your pH of 2.6 here is relatively close to 3. That is a pattern that you are going to notice, especially when you jump into acids and bases. So it can be a little bit of a logic check, which can help and make sure that your answer is in the right ballpark. Okay, so here we solved for pH, but what if we wanted to solve for concentration? So let's take a look at this example. We want to solve for concentration, and we are given the pH. So I want to use the exponential form right up here because I have pH and I want to solve for concentration. So let's just write that form down here and plug in our value for pH. So we have our concentration is equal to 10 to the negative 8th, which means our concentration is 1.0 times 10 to the negative 8. Yes, that's not a mistake. A pH of 8 equals a concentration of 10 to the negative 8. This is just a really cool thing about logs. Okay, here is another example, same thing. We want concentration. We have been given pH, so I'm going to use the same form of the equation. So my concentration is equal to 10 to the negative 6.75, which means my concentration is equal to 1.78 times 10 to the negative 7th. And no, that's not a mistake. The 7 here is very close to the 6.75. It's not exact, but it's close. And just recognizing that pattern again will help make sure that your answers are making sense. So as you saw with those last few examples, we often use logs when we're dealing with acid-base chemistry, but they do also show up in equilibrium calculations as well. Now, if you need refreshers on other math topics, you can check out these videos here, and thanks so much for watching.